Welcome. In this video, we will take a look at section 7.1, looking at the law of sines. So this is the first section on really non-right triangles and how we work with them. We've worked with right triangles a lot with our trig functions, and now we're going to apply these trig functions within the context of a non-right triangle. So let's consider the law of sines. For any triangle with angles A, B, C and side lengths little a, little b, little c, this relationship of sine A divided by A minus the sine of angle B divided by B is equal to sine of angle C divided by side length C. And obviously we can flip this and take the reciprocal of this ratio and it would be equivalent as well. But this is just telling us that the sines of angles and their opposite side are in ratio equivalent to all the other angles and sides. So this is a really helpful tool to be able to solve for unknown sides and angles of a oblique triangle. So any non-right triangle is really referred to as an oblique triangle. So it's close to the word obtuse, but it means something different. Oblique just means no right angles. So we can remember the word oblique. We can use the law of sines with the oblique triangle. So let's consider the example below, and we'll apply the law of sines to this first triangle. So we're going to consider a triangle ABC where the angle A is 30 degrees, the angle B is 70 degrees, and we're given a side length A equal to 8.0 inches. Use the law of sines to find angle C, side length B, and side length C. All right, so let's first just write out a little sketch to help us. We're going to have a triangle. And this triangle will try to build in a 30-degree marker at A. We'll call this our 70-degree marker at angle B. And here will be our angle C. Again, that's not guaranteed to be a right angle. We would have to go out and find that. And we know that side length A is equal to 8. We would have side length C and side length B right there. All right, so we have 3 knowns and 3 unknowns. And so we're going to start by looking at the angle. Since we have 2 known angles, we could go out and solve for angle C by just the property of a triangle. We know all triangles add up to 180 degrees, and we have a 70-degree angle and a 30-degree angle, which adds up to 100. So subtracting 100, we get the final angle to be 80 degrees. So we have a 80 degrees for this last angle. So that was one portion of our problem. And now let's go for those side lengths. Now we can use the law of sines to figure out these side lengths. So let's consider using the side length that we know, which is A is equal to 8, the angle A, and then we're going to go for using the capital B angle to solve for our B side length. So let's set it up like this. We have A, which is 8, divided by the sine of 30 degrees, that's the sine of angle A, is equal to the B length divided by the sine of 70 degrees. So this is just one portion of the law of sines. We just want to set one ratio equal to another. And now we're going to just solve for that single variable. We can do that by just multiplying both sides by sine of 70 degrees. So sine of 70 degrees will cancel on the right side, and we'll just be left with that b. So let's write that out one more time, and we'll find our approximation. So b is equal to really 8 sine of 70 degrees divided by sine of 30 degrees. Now we'll make sure that our calculator is in degree mode here. And for this one, we'll just round to the nearest tenth for our purposes here. So if we round to the nearest tenth, we will end up getting 15.0 for that side length, rounding to the nearest tenth. And so we have the side length b solved for, that's going to just be 15.0. The next side length that we can solve for is the last one, side length c. And so we're going to use the same ratio to start with the side length a and angle a. So we'll start with 8 divided by sine of 30. That's the ratio that we would get for the a side with the a angle. And then divide is equal to our side length c divided by the sine of 80 degrees. That's the c angle. Again, we'll multiply here by the sine of 80. Because again, sine of 80 is just a number. It's a constant. So we'll multiply that on both sides. That will cancel on the right, leaving us the side length c. And so we'll write this one out one more time as well. That c is going to be equal to 8 times the sine of 80 divided by the sine of 30. And if we put this into our calculator and round to tenth or 1 decimal, we'll find this to be equivalent to 15.8. 15.8. So side length C is the largest side length here. And each of these are in inches when we solve for them. So we'll make sure that's labeled there. In inches. I want to make one point on our solutions here before we move on. Notice that the side length C is the largest, as I said before, and that corresponds with the largest angle. The smallest angle is angle A at 30 degrees, and that corresponds to the smallest measure of side length. So that's a good check to make after you're done with a obtuse triangle like this. Make sure that your larger angles correspond to the larger side lengths. So that completes this problem, and we'll take a look at a second law of sines problem next. So in this next problem, we have solved the triangle ABC if B is equal to 34 degrees, C is equal to 82 degrees, and side length A is 56 centimeters. So again, let's try to draw a picture here. We'll have a nearly right angle at the top and a 34-degree angle somewhere at the bottom. So we'll call this angle B, 34 degrees, angle C with 82 degrees, and then we'll have a final angle of A, which is unknown. And then we have the side length A equal to 5.6, side length B, and the side length C. So let's consider again law of sines here. Notice the pattern that we are given, and later on this will be important when we need to choose between the law of sines and later what we'll learn about the law of cosines. Notice that the law of sines is used when we are given two angles and a side length here. Two angles and a side length. So that's just a comment there. So let's continue with this problem and go out and find that final angle to start. Angle A, we can consider again the triangle adds up to 180 degrees. If I add up 82 degrees plus 34 degrees, this is a total of 116 degrees. And if I subtract that sum to 180, or from 180, we'll end up getting the final angle measure at 64 degrees. So 64 degrees will be that final angle measure of A. So that's our first solution. And now we'll walk through solving for angle or side length A, or side length B and side length C. Excuse me. So we'll start with side length B. So we'll start out with the ratio of side length A. That's 5.6 divided by the sine of 64. That's our known angle 64. This has to be equal to the ratio from B. That's B divided by the sine of its opposite angle, which is 34 degrees. So we're starting with solving for B. Again, we can multiply by the sine of 34. That's just a constant number. So we have the sine of 34, sine of 34 to multiply by. It'll cancel on the right side and we'll be left with that B side length. Right? And if we put this ratio into our calculator, be careful that we're in degrees again. We'll round this one to the nearest tenth again. This side length B should end up getting 3.5 centimeters. 3.5 centimeters. The last calculation we'll do is for C here. The side length C is the last one to solve for. We'll start with the same ratio for A, because that is our known ratio. So the reasoning behind starting with the angle A ratio is because it's known to us, and so we're not using a rounded value. If we were to use the 3.5, we know that's a rounded value, so our final result for our next side length would also be a rounded value. So we want to stay away from that as much as possible by just going with the givens when we can. So we have 5.6 and sine of 64. This is equal to, we'll have side length C, and then we'll have the C angle, which is the sine of 82 degrees. And again, the pattern here is to multiply by that sine of 82 degrees to solve for C. And so these will cancel, and I'll just be left with that product on the left, where C is equal to 5.6 sine of 82 degrees divided by sine of 64 degrees. I'll give you a moment to put this into your calculator. 5.6 times the sine of 82 divided by the sine of 64. If you're able to put this into your calculator, we'll round this to the nearest tenth again. We should get 6.2 centimeters. You can confirm that in your calculator, 6.2 centimeters. And that would be the completion of that problem. We have our two side lengths, side length C, side length B, and we have the angle A from our first step. All right. Next, we'll take just a look at an application problem involving the law of sines. All right, so let's consider. A man standing near a radio tower antenna observes that the angle of elevation to the top of the antenna is 64 degrees. That's this first placement right here. He then walks 100 feet away, further away, and observes that the angle of elevation to the top of the antenna is 46 degrees. That would be our second position right here. Find the height of the antenna to the nearest foot. Okay, so let's consider what we have here. If we can solve for a height of an antenna. So one thing that we might want to be able to solve for first in solving for this height of an antenna is thinking about solving for x. Because eventually we'd like to have a ratio for this big right triangle. So let's think about kind of the end of this problem. Our goal is to find the height h. We do have the angle here, 46 degrees. So if I was to utilize that 46 degrees, since this overall is a right triangle, we would know that if we were able to find x, we could set up a ratio that said that the sine of 46 degrees is equal to, well, that would be opposite, that's the h, divided by the hypotenuse, which happens to be the x. So ultimately, that's kind of where we want to get to. So we'd like to solve for both, x, and then we'll be able to solve for h using a simple sine function. So let's consider the triangle that's represented by this outline in red. Actually, we won't use red since red is already used. We'll outline this in the purple color. This oblique triangle that we're outlining here might be of help to solve for that x side. All right, so let's take a look at kind of replicating the sketch of that triangle over here as much as we can. So we have this triangle on the right. This is our x. This is 46 degrees. And we have an unknown angle here and an unknown angle here at this point. But we do know that this angle over here is 64 degrees. So let's first consider how we could use these angles. And again, we have these measurement of 100 feet on this one side. So if I could solve for a few of these angles, I think that would be really helpful here. So let's see if we can solve for the additional angles and then set up some law of sines to finish it off. Since this is a straight angle down below, we know that this has to add up to 180. So if I take 180, that straight angle, and subtract the 64 degrees that's already there, I can find that this angle interior is going to be 116. So we have 116 degrees. I didn't draw it perfectly, but it should be a little bit wider. But it's 116 degrees in that interior angle, which we can then turn around and solve for my final angle up at the top. So I currently have 116 degrees, and I have a 46 degree angle in my triangle. This will add up to 162. And so the remaining angle in that triangle, if I subtract from 180, is going to be 18 degrees. So I have all the angles in that oblique triangle, 46, 116, and 18. All right, so let's consider now what law of sines ratio could actually help us here. I can consider that I have one side length, which is the 100. That corresponds to the angle of 18 degrees. And I'd like to go out and solve for x, which corresponds to the 116 degree angle. So those are the components that I like to set up in the law of sines problem. Ultimately, again, we're trying to solve for h, but we need to solve for that x coordinate, or the x length first, to be able to get that done. So let's set up the law of sines here. We'll start with the known ratio. We have 100 feet divided by the sine of 18 degrees, that's the opposite angle, has to be equal to the x side length divided by the sine of 116 degrees. And it's a good idea to, if you're solving for side lengths, it's easiest to write the side length on the top of the ratio. It just makes the algebra a little bit easier. So again, let's take a look at multiplying by sine of 116 on both sides. And if we do so, we'll have sines of 116 will cancel, and we'll have x is equal to, here, this will be 100 times sine of 116 divided by sine of 18 degrees. All right. This is certainly a constant number, and we could put this into our calculator right now. One thing that we can do, though, is just leave this in its exact format for just the time being. And again, come back to this original equation that we were thinking about. The sine of 46 degrees is the ratio h divided by x. Now, let's just input this quantity right here in for x. And we'll just write this out in one statement and then put it in our calculator once. So we know the final result here is the sine of 46 degrees is equal to h, that's an unknown we'd like to solve for, divided by 100 times the sine of 116 divided by the sine of 118, or 18 itself. Now, to solve for that h quantity, all we need to do is multiply by the reciprocal of the bottom, or we'll just multiply by that fraction. So let's take a look at multiplying by that. So we'll just multiply both sides by that 100 sine of 116 sine of 18. So we'll have 100 times sine of 1/16 divided by sine of 18 degrees. And those will cancel, just the multiplication of that and that in the numerator. And if we put this, all this right side here into our calculator, we'll find the value for h. And so h here, you can confirm this in our calculator. If we find this out, this ends up being the 100 sine of 1/16, I'll confirm this with you guys, times the sine of 46, and then divided by the sine of 18. This is in degrees in your calculator. You will end up getting approximately 209. We'll just round to the nearest foot here. Feet. 209 feet. So it'll be like 209.22. And so that would be the height for us. So there was kind of two calculations going on, really. When we put them together, there was that law of sines to solve for our x quantity. And then we use that x quantity to put into a sine function. Again, the sine of 46 degrees in that big right triangle would be the opposite, which is h, and the hypotenuse of that large triangle, which would have been x. So that's the completion of this problem. We should go away with 209 for the length of the antenna. And that completes this video on section 7.1. So thanks for watching the video, and I will see you guys in the next one.